Hey everyone, Mr. Fransky here. Today we're going to talk about Euler's method, and the way you pronounce this is Euler, kind of like Euler, O-I-L-E-R, right? Looks like Euler, but Euler was a super smart mathematician, did a lot of great things for math and calculus, and so there's this method that's named after him. It's an approximation method, so kind of like using rectangles or using linearization. In fact, this is a lot like linearization. And it kind of goes along with the idea of slope fields, where you don't have to know the solution to a differential equation to be able to know something about the solution function. So today we're going to be able to use Euler's method to approximate function values of a differential equation. So let's see what's going on. So vocabulary: Euler's method, linearization, differential equation, and over-under estimate. These are many important things. So how Euler's method works. So we have some differential equation. dy dx is equal to something. Okay, so you can make a slope field out of that, right? So you can make a slope field. You can like what different slopes are, different places, whatever is going on. I don't know. I'm not sure. Okay, and you can kind of get an idea of what a solution curves look like, right? So it's like, let's say you know the solution through your particular point is going to look something like, I don't know, like this. Okay. All right, but you don't know exactly what it is. And let's say that you know it goes through a certain point. Let's say that point, we call it our starting point. Let's say it's like, I don't know, it looks like I graphed it about 2, 1. Okay, so that is the initial condition. Initial condition. Looks really bad. Initial condition. But that's the only point that you know it goes through. Okay, so that's the initial condition. So then the question is, well, using that point, could I like find out what, so let's say the solution curve is f of x. Could I find out like what f of 3 is? Well, not exactly, right? Unless I can solve the differential equation, I can't exactly find out what f of 3 is, but using the differential equation, I could say, well, what if we used a line at that point? Right? What if we used a line at that point to approximate f of 3? That's linearization, right? If we used a line, then we could get the line. And the way that a close approximation to the point. And the way I drew it here, it looks like that would be a slight underestimate, right? If we used a line, it's because the curve is concave up, the tangent line lies underneath. It'd be a slight underestimate. And so what Euler's method is basically a way to say, well, what if we did like linearization a bunch of times? So let's zoom in on that part right there. Okay, so let's say this is our curve. Let's say this is 2, 1. And we want to know what f of 3 is. Let's say 3 is over here. So instead of just doing linearization, where that just would be using a single tangent line to say, well, f of 3 is approximately this value. And to do that, all you need is a point, which we have, and a slope, which you can get from the derivative. Instead of doing that, what you do is say, let's split it up a little bit. So let's say you split it into 2 pieces. So here we have 2.5, here's 2. So let's approximate 2.5 using that tangent line. So that's going to find the point right here. And now, instead of going all the way out to 3, we're going to use a different tangent line. Okay, so I'm going to kind of make this smaller. I'm just going to go right to there. So we use a different tangent line. We're going to use the slope of the curve at 2.5. Now, we don't know what the coordinates of the exact point are at 2.5, but we know the slope because we have the differential equation, right? So what we're basically doing is using a different tangent line now. And the tangent line would be tangent to the curve at this point, but we don't know that point, so we use this point instead. So we're going to be a little bit off. And the more steps you use, the further away you'll get from the curve, right? If you wanted to go out like to 4, it's going to get further and further away, right? But as long as it keeps curving upwards, if you use more steps, it'll be more accurate, right? What if I used 4 steps instead? So if we get rid of this, so what if you went every quarter? So use this tangent line for a little bit, then you use a new tangent line for a little bit, then a new tangent line for a little bit. And what happens is you kind of follow the curve. It's not exactly on the curve, but it's close. And how can you get better? Well, use more steps. The more steps you use, the shorter you're using a tangent line. So you're going to be closer to the curve, right? And every time you use the new derivative at your new point, and so that's going to curve your little lines up a little bit more. Okay, so this is the general idea. So one more picture I'm going to draw here. So if we imagine how we can find these differences, okay? So this is your starting x point. I'm going to call it x0. Then you're going to go towards x1 right here. And the difference between those we call delta x. Okay, and delta x is some known value. If you're going from 2 to 3 using 4 steps, delta x will be equal to 0.25, right? Because you're going from going 1 using 4 steps, so you're going 0.25, 0.25, 0.25, 0.25. And then what you want to know is how much does the y change? So we have y initial, and we want to know how much does the y change. So if we use a tangent line, okay, we're kind of creating this triangle right here. right? So delta x is the bottom of this triangle. I want to know what is delta y. Now, it's not the actual value, right? The actual value is up here on the curve, but I can do this by using the slope of that tangent line, right? The slope is the change in y over the change in x, and the slope of that line is just equal to the derivative at the x0 point right here, right? Because we're using a tangent line. So this is f prime of x0, which we can get because we have the derivative. We know what the slope is, right? So if I want to know delta y, I just multiply by delta x. It's going to be the slope times delta x. Then what we do is we just restart with that new point. So this new point is going to be x0 plus delta x and y0 plus delta y. We use that and we do the whole thing over again. Now we use the slope at x1, right? So this term's kind of complicated, but when you actually do this, this is not hard at all. So let's do it with an example here. So we have a differential equation, x plus y. This looks kind of like the ones that we did the slope field with before, right? This would have a really hard solution, but it's very easy to linearize. Very easy to make a slope field too, right? So what we're going to do is we have our starting point. So they tell us 1, -1 is on the particular solution f of x. They want us to use 4 steps to approximate f of 3. So let's kind of draw what's going on. I don't know what the curve looks like, but they tell us 1, -1 is on the curve. Let's say the curve is like increasing concave down. I don't know if it is or not, but maybe it is. They want us to find f of 3. Here's 3. They want us to approximate that using 4 steps. So if we're going a total distance of 2x units, we use 4 steps, then our delta x is going to be 0.5. So we move 0.5 every time. So 0.5, 0.5, 0.5, 0.5. And what we want to do is we want to figure out what approximation we have for f of 3 when we use tangent line, tangent line, tangent line, tangent line. Okay. So what I always do here, I always write the same thing out. I write start. And then we have, let's see here. So our starting point in this case is going to be 1, -1. And then what I have next is I'm going to have the derivative of that x value. So I usually call this m, because that's going to be my slope. So really what this is, it's going to be f prime of whatever that x value is. So I write x0 because that's the starting x value. And that's going to change every time because I'm going to have different x value as we go. Okay, then after that, I'm going to write my delta x, and delta x is never going to change. So in this case, delta x in this case is always going to be 0.5. So it's going to be 0.5 every time. And then we have the delta y, which is just m times delta x, right? We showed that on the last one. It's just the slope times the change in x is going to tell us how much we change for the y value. And then we're going to have our new point. So our new point is going to be x plus delta x and y plus delta y. That's how much the x changed and how much the y changed. So let's see if we can do it. So here we have our starting point, 1, -1, and I really shouldn't, I guess, put f prime of x0 here because this differential equation involves x and y. So you could write dy dx here, right? This is dy dx because it's the slope, it's the derivative, slope of the tangent line. Okay, so the slope at this point is going to be x plus y. That's 0. Well, that's easy. Delta x is 0.5. So it looks like we're at a max or a minimum point here maybe because the slope is nothing. Now delta y is m times delta x. Well, that's 0. Now we have our new point, x plus delta x, that's going to be 1.5. And we have our y plus delta y, which is still -1. And that's our new starting point. So now we have 1.5, -1. So the y didn't change at all because we had a max or minimum. So we said, well, if you use the tangent line, then the y isn't going to change. The x moves on, but the y hasn't changed at all. Now we're going to use whatever the slope is at the next point. So the slope this time, if we add them together, is 0.5. Change in x is still 0.5. Change in y is the slope times the change in x, which is 0.25. So now we have our x plus delta x. So that's going to be 2, and our y plus delta y. So -1 plus 0.25 is -0.75. So you must be increasing, right? My pictures are bad because I have no idea what this looks like, but it doesn't matter. All right, so our new point is 2, -0.75. So our slope there is x plus y. That's gotten from the differential equation. So 2 minus 0.75 is 1.25. Change in x is 0.5. So at this point, I'm going to grab a calculator because AP usually asks questions where you don't have to use a calculator. They'll give you calculations that are easy enough to do with the decimals, and sometimes the last one might be a little bit tricky, but they won't ever give you anything you can't handle. But for this problem, I'm going to grab a calculator. So I'm going to do m times delta x. That's 1.25 times 0.5. That's 0.625, so that's my change in y. So my new point, 2.5, right, because it's just x plus delta x. We march on with that 0.5 every time. And the y coordinate is going to be -0.75 plus 0.625. And that gives me -0.125.
Okay, so now that's our new starting point. So we have 2.5. This should be our last step here because we're just going to f of 3, negative 0.125. And so our slope now, if I do x plus y, so 2.5 minus 0.125, that gives me 2.375. Change in x is still 0.5. And then if we multiply 2.375 by 0.5, that gives me 1.1875. So finally we get to 3, and then let's see, negative 0.125 plus that answer I just got is 1.0625. All right, so f of 3 is approximately 1.0625. Got to make sure you use squiggly equals because it's not exact, right? We used a bunch of tangent lines to figure that out. Now, if the graph that I drew is accurate, which we're pretty sure it's not based on these values, if it's concave down, remember tangent lines would be on the top. So if we're using like a bunch of tangent lines and we know the graph is concave down the whole time, that would be an overestimate. Right? If it's concave up, then all of our tangent lines are on the bottom. That would be an underestimate. So Euler, just like linearization, depends on concavity, if you're concave up or concave down. And again, just draw a picture to be able to see that. All right, let's try another example. Okay, so this one we got our differential equation is 2x minus y, and we're using 5 steps starting at 2, 3 to approximate f of 1.5. Interesting. So if we're at 2, 3, 1, 2, 1, 2, 3, and we're trying to find out f of 1.5, looks like we're going backwards. So our delta x here, each time, if we're going back 5 steps to 1.5, delta x will be negative 0.1 each time. Okay, so let's jump in. So we have our start. We have our m, which in this case is going to be 2x minus y each time. We have our change in x, which we know is going to be negative 0.1 every time. And then we have our change in y, which is m times delta x. So we're starting at 2, 3. 2x minus y. Let's see, 2 times 2 is 4 minus y, 3 is 1. Times negative 0.1 is negative 0.1. So our new point is going to be 1.9, right, because we lost 0.1 from the x. And then our y coordinate is going to be 3 minus 0.1, which is 2.9. All right, so that's our new starting point, 1.9, 2.9. And so this time, let's see, 2x minus y. I'm going to grab my calculator for that. So 2 times 1.9 minus 2.9 gives me 0.9. Change in x is still negative 0.1, so multiply those, that gives us a negative 0.09. So our new point, 1.8 for x, because we keep losing 0.1. And the y, if we have 2.9 and we subtract 0.09, that should be 2.81. All right, so that's our new point, 1.8, 2.81. So 2x minus y, so 2 times 1.8 minus 2.81 gives me 0.79. Change in x still negative 0.1, so our m times delta s will be negative 0.079. New x coordinate, 1.7, keep dropping 1 there. And the y coordinate is going to be, let's see, 2.81 minus 0.079 gives me 2.731. Uh-oh. 2.731. Okay. All right, so that's our new starting point, 2.731. And so then 2x minus y, so 2 times 1.7 minus that answer I just got. Use my grabbing function in my calculator. That gives me 0.6, is that right? 2 times, yes, 0.669. Okay, so negative 0.1, 0.1 for our change in x. So that gives me a change of negative 0.0669. So we have 1.6. And then our y coordinate, let's see, 2.731 minus 0.0669 gives me 2.6641. One more time. So we have 1.6, 2.6641. Let's see, 2 times 1.6 minus 2.6641 gives me 0.5359. Negative 0.1 again, so we have negative 0.05359. And if we do x minus 0.1 is 1.5 now, so we finally got to our our x value that we want. And then our f of 1.5 is going to be approximately 2.6641 minus that 0.05359, which is 2.61051. Now, of course, we want to make sure to 3 decimal places at least, but this is an exact answer, so I might just skip the whole thing. So f of 1.5 is approximately equal to 2.61051. So approximation again, of course, and we don't know anything about the second derivative here. Sometimes they'll ask you to find the second derivative using implicit differentiation. You'll actually see that on one of the worksheets you're going to get. But in this case, we don't really know what the second derivative is, but if it was concave up, again, Euler's method is an underestimate because it's going to try to keep up with the curve, but it can't. Concave down, going to be an overestimate because it's going to try to stay down with the curve, but it's going to be too high because those tangent lines will be on top of the graph. All right, that's it for Euler's method. So as long as you make the chart, really not too bad. Love you guys. That's why I'm here. Have a great day.